So let's do one more circulation greens where we do the another region with holes. So I mentioned that greens, even though it says you need it simply connected, the truth is you can do greens with holes. And I think I mentioned when I showed you the hole situation here, as long as you go around the border counterclockwise and then you go into the hole and then you go around the hole clockwise and then you come back out where you end up. This will also work for situations where you have more than one hole, just to let you know. Let's say here's your region R, and let's say you had 2 holes in there. Okay, how would you apply greens here? Let's say here's the starting point. You first go around the outer border in a counterclockwise direction, call that curve 1, and then you head in to the first hole, call that C2, and then you go in the clockwise direction, like so, this way, but you only get halfway there, like this, C3, and then you make another slit, and you go into the other hole, call that C4, then you go all the way around the inner hole going clockwise, call that C5, then you come back out, call that C6, and then you finish the other half of that hole, call it C7, and then you come all the way back along that other slit that you made in the region, and then call that C8, and you're done. So the curve would be the union of all 8 of those curves, and then greens would apply. So you can do this for as many holes as there are in the region, fine. So here is a region with holes, because check it out. They want this inside this ellipse, but outside the circle. So there's your circle centered at the origin, radius 1. And I think we already did this when we divided both sides by 36. We got x squared over 9 plus y squared over 4 equals 1. That's an ellipse equation centered at the origin, where the x-intercepts are -3 and 3, and the y-intercepts are 2 and -2. So here's our ellipse. So the region is this region here. It's got a big old hole in it. Fine. So how do you do greens? Well, you're not actually going to do the line integral because you're going to use greens. You're going to turn it into a double integral over the region. And the region kind of looks like a donut. And then you're going to integrate dn dx minus dm dy. Okay, let's find that out right now. So m is the first component and n is the second component in your differential form. So what is dn dx? The derivative of 2x plus x squared with respect to x.
2 plus 2x.
Yeah, so you're going to go 2 plus 2x. Okay, minus dm dy. So take the derivative of 2xy with respect to y. What do you get?
2x.
2x. Okay, hey, something good happens, which is kind of nice. These 2x's cancel, and we're just integrating this double integral of a constant. But I can pull the constant out. It's just a multiple. And then I want you to notice that this double integral, I'm not even going to bother iterating it. Not going to convert to polar, not going to do any of that. Don't need to. Because you guys know that a double integral with a 1 as its integrand represents what?
Area.
Area. And so what am I saying? Well, this is 2 times the area of this region R, where it's a donut. So how are you going to get the donut region? And I should ask Vanessa here. Vanessa, I don't want to put you on the spot, but do you remember we did something like this? I don't know.
Yeah.
You remember it was take the area of the outside region and then subtract the area of the inside region?
Yeah.
Yeah, so this is going to be, we're going to have 2, and then we're going to have area of the ellipse, because that's the outer curve, minus the area of that inner circle. Okay, and you guys now know how to find area of an ellipse because I taught you last lecture, pi AB, and of course you know how to find the area of a circle, pi r squared. So this is going to be 2 times pi, a is 3, b is 2, pi r squared. This is just a unit circle, so the radius is 1. And then you're going to go, okay, that's 2 times 6 pi minus pi, but that's 2 times 5 pi. Oh, wonderful, it's 10 pi. So because it's a positive number, that means that if that vector field, you know, if you can imagine it represented, you know, some shallow pool, jacuzzi of moving water, the little paddle wheel would indeed be spinning in the counterclockwise direction, and the magnitude of that gives us the idea of the speed of it. Okay, the speed, how fast it would be spinning. Okay, so that's it. Regions with holes. And yes, that's going to be on midterm 4. And yes, it's going to be in the final. I'm really into regions with holes. In fact, I was so upset that Briggs didn't cover it. I made some of my own custom made questions so that you would get regions with holes in my math lab. So it's kind of a pain in the butt to make these custom made problems, but you're worth it. Okay.
You're too much, Rasky. Thank you.
I know. I do so much for you. You know, one of my friends would go, "Hey, I wish you'd stop doing me so many favors. Just stop it." Okay, there's another version of greens. And yes, you need to know it. It's not that hard, but it computes flux instead of flow or circulation. It's a flux integral. So here's the idea. If you can still picture that bathtub water or the jacuzzi flow as your vector field, then if you had a curve, you know, that you drop into your bathtub and you submerge the curve in your bathtub of water where your velocity is representing that force field, how much water is flowing outward from the curve versus how much is flowing in. So that's called flux. So if you get a positive flux, that means more water is flowing outward from the curve than flowing in. If you get a negative number for flux, that means more bathtub water is flowing into the curve than is flowing out. And if you get a zero flux, that means the amount of water flowing out of the curve is canceling the amount of water flowing in. So you get sort of a net of zero flux. Okay? So remember that the line integral that you've done so far was the dot product of your force field with a unit tangent vector, because you wanted to know, that was when we were projecting circulation. You wanted the force field and have it projected onto the unit tangent vector all the way around the curve. But now we want to do a different thing. We don't want to project the force field onto the unit tangent vector to get that circulation flow. We want to project the force field onto a vector that's normal to the unit tangent vector. Can you say principal unit normal vector? Yes. So we're going to do that. We're going to take a dot product of the force field with the unit normal vector, and that's going to basically give you the scalar component of the projection of the force field onto the unit normal vector. So the way they do that is, well, how do you pick n? And you want to pick n so that it's directed outward from the curve. So they're talking about how you would do that, and you still keeping the fact that the dot product of t and n still has to be 0. That means t and n are orthogonal. So remember that big T looks like this. It's the unitized version of speed, and you need to know that for the final. So know this for the final. Know for the final. It's going to be on the final. Then what? Well, n, you want it to, if you don't want to go through all the rigmarole of getting n because you're lazy, it takes some time. You got to go get t prime, and then you got to unitize t prime. But here it's like, let's just pick one that'll make it dot product of 0 and have it outward. And so they do it this way. So now if you're going to do this line integral, and this is the flux line integral, where you're calculating the amount of water flowing out or in, you're still taking a dot product, but this time you're going to take the dot product of your vector field with the unit normal vector. ds is still the arc length element. It's not like, oh, integrate with respect to s. No, ds means arc length element. And so what is that arc length element? We already went over that in the first 5 minutes of class. Go.
Speed.
Speed element.
Speed. R prime and then dt, because we're going to actually integrate with respect to t, not s. Okay, then when you do the dot product, this m multiplies with the y prime here. By the way, these r primes cancel. Okay, excuse me, the speeds cancel. I mean, if you take this scalar and distribute it over this vector, these r primes, they're gone. So what do you have? You have m multiplied with y prime of t, which is dy dt, but then this dt cancels that dt. So you just end up with m dy. Similarly, since there's a minus here because of the orthogonality, you minus n dx. And so that, does this look familiar? Keep in mind, this is not m dx plus n dy. Do you see how it's different? How is it different?
The sign.
But there's even more that's different. Look very closely. It's important that you get this, otherwise you're going to screw up on midterm 4.
Oh,
Do you notice that in the regular differential form, we had m multiplying with dx?
yes.
And n gets multiplied with the dy, as well as there being a plus sign in between. Big difference with this puppy. Your m is multiplying with dy, and yes, there's a minus sign there, and your n is multiplying with dx. That's called a flux line integral. And if you apply Green's to it, you still are going to turn it into a double integral, but the integrand is different. So I claim that if you had applied regular Green's to it, the one that I already taught you, it would have come out to this. Let me just show you why in slow motion. So if I rewrite that line integral as something multiplied with the dx first, because that's kind of how the look is for differential form, and then plus the m dy like that. So when you apply your knowledge of regular Green's, you turn this into a double integral. And so the whatever is this guy here, that's sort of your new m, if you will. You take the derivative of that with respect to y. So you go, negative dn dy, and then then you go minus like this. How do I want to do this? Let me do it the other way. See, because I'm getting a little confused here. So normally you would go dm dy minus dn dx. Okay. So this is your new m. So you're going to take the derivative of him with respect to y. So you're going to go, okay, minus dn dy. And then you're going to go minus dn dx, but then that's this guy here. So you're going to go minus dm dx. Well, this is kind of not working out. It's got to be a plus. I'm doing something wrong here. What am I doing? Let me put this on hold for a second while I stop. Hit cancel.